Welcome to E544 on Tuesday, March 25, 2014.
Thank you very much. Good afternoon, everybody, and welcome back again. Hopefully all you had a very pleasant spring break, but all good things have to come to an end. We are back to the grind. Okay, now I need to have 30 minutes more to wrap up the material on the modulation techniques before we get into the circuit designs of different components of the transceivers. Okay, we were looking at that time. The type, can you zoom back please a little bit? Let's review quickly from last time. We started looking at different types of QPSK. QPSK stands for what? The quadrature phase shift king. Quadrature phase shift king. Every signal or every symbol is representing how many bits? It's representing 2 bits. In the conventional QPSK, the phases are what? 45, 135, 215, and what? 3 what? 305? 315. Or, of course, what? 0, 90, 180, and what? 270. By the way, keep in mind, rotating the axis does not affect the probability of error. The probability of error will be what? Will be the same. Okay. Now, all the points, by the way, are located on a circle. Why? Because the amplitude is what? It's constant. This is a what? This is a modulation is onto the what? Phase. However, the problem that we saw in here last time was what? The problem is that during the transition from one symbol to another symbol, if there is a what? 180-degree transition, then the transition will go through what? Through the origin. Are you following me or not? Resulting in what? If it goes through the origin, resulting in the amplitude equal to what? 0, which means the receiver will have hard time what? Establishing or maintaining the synchronicity with the transmitter. If there is nothing there, he would say, what happened? Nothing there. Clear? So we said what? We said we try to avoid the transition from what? The 180 degrees transition. The 90-degree transition, is there an amplitude change? The 90-degree transition, in other words, going from here to here, is there an amplitude change or a slight one? A slight one. Why? Because remember, this is located on a circle, but the transition will not be on the circle. The transition will be what? Abrupt between the phases. Clear? But the degradation is just a little bit. Are you following me or not? Not much, just a little bit. Now, one way to get rid of the 180 degree is through the use of what? Offset QPSK, or what is known as what? Staggered. Another name for it is what? The staggered QPSK. In a staggered QPSK, one of the channels, either the I channel or the what? The Q channel, is delayed by how many bit? By a duration of what? 1 bit, not one symbol. By the way, if you delay it by 1 symbol, then you haven't done anything. Do you agree? If you delay it by 1 symbol, then you haven't done anything. The problem is still there. You delay it by what? 1 bit. Remember, every T sub S, which is the symbol duration, T sub S is equal to what? 2 T sub B. So when you delay it by 1 bit duration, it means what? You are delaying it by 1/2 symbol duration. Clear? You eliminate what? You eliminate the possibility that you are going to go what? 180 degree. The transition is either what? 0. 0 means what? This is the symbol, current symbol, and the next symbol is what? Is the same. And the what? Plus or minus what? 90 degree. Clear? This one gives a what? Gives a better performance as what? As far as what is concerned. Not as far as the bit error is concerned, not as far as the bandwidth occupancy is concerned, but as far as what? As far as the requirement for what? For the power amplifier to be strictly what? Linear. This one, you can what? You can loosen up that constraint, and you what? And do not worry about what? The recreation of what? Of the side lobes much. If the power amplifier is work in the nonlinear region. Did you get this or not? Always remember, in a power amplifier, which we'll talk about it in about 30 minutes, in a power amplifier, when the power amplifier operates in a nonlinear region, your spectrum will what? All of these side lobes will show up again. And when they show up again, you are going to cause what? Adjacent channel interference into the adjacent operators. Did you get my point or not? You don't want that. You want your emission to be confined within your band of interest. Clear? No response. Clear? Okay, good. Now, the third type, which we discussed last time, was what? Pi over 4 QPSK. In pi over 4 QPSK, don't get fooled by seeing what? 8 signal set. In reality, what do we have? We have 2 constellations, each one with how many signal sets? 4 signal sets. Those 2 constellations are what? 45 degree out of phase. Did you get my point or not? And for every symbol, you are going to choose a signal set from a what? A constellation. For the next symbol, you use a what? A signal set from what? A signal from which set? From the second set. Did you get this or not? Which means what? It means that there is no way you are going to have what? A transition. 0 degree. Do you agree with me or not? Why? Because you are going to switch or alternate between one constellation to another constellation. Clear? Clear? You eliminate the 0. But you also eliminate the what? The 90 and the plus 90 and replace them by what? Replace them by what? 40 plus or minus 45 and plus or minus what? 135. Did you get this or not? Okay. This is the one that they showed that is a little bit better than this one. Again, not in terms of the probability of error, not in terms of what? In terms of the bandwidth occupancy. Those are the same because we are still, every symbol is representing how many bits? 2 bits. But in terms of what? In terms of easy of what? Easy in synchronization. Why? Because there will always be what? A transition. Remember, in this one here, if a symbol is followed by the same symbol, there is no what? There is no transition. There is no phase difference. Clear? And if there is no phase difference, if there is no transition, it will be a little bit harder on the receiver to maintain what? Synchronicity for the symbol detection. Clear? Clear? This is the one that was used in the 2nd generation digital cellular in the US, not the GSM. This is what is known as what? IS-54. AT&T developed this one, and it uses in what? In its 2nd generation, which is what? TDMA based. TDMA stands for what? Time division, multiple access. By the way, so is GSM. GSM also uses what? TDMA. However, in GSM, the bandwidth allowed is bigger, which means they allow them to use techniques which are not bandwidth efficient, but are what? Power efficient, so that they can use the what? The power amplifier in its what? Nonlinear region. In here, the bandwidth was what? Limited. So they forced them, the FCC, the government of the US, the FCC, forced them to use what? To use a modulation technique, which is what? Bandwidth efficient. Which is what? Which is the QPSK. The QPSK is a bandwidth efficient as opposed to the what technique that is used in GSM, which I will show you in just a second. Clear? Oh, we discussed this all last time, and I showed you all of these things, and so on and so forth. By the way, you notice the degradation of what? Degradation of the side lobes. And you will see in a minute when I show it to you compared to the QPSK, you will see that this one is what? Faster. The side lobes will what? Will degrade faster, at a faster rate. Clear? Okay. The main lobe, by the way, will be the same or different? The main lobe between the QPSK and the staggered QPSK and the pi over 4 QPSK. The main will be the same. The bandwidth is still the same. And the bandwidth efficiency, theoretically, what do I call it? 2 bits per second per hertz. The bandwidth efficiency, theoretically speaking, is what? 2 bits per second per hertz. Why it is 2? 2 because every symbol is representing how many bits? 2 bits. Clear? Okay. Let me ask you a question. Jump a little bit, and I need to make sure that you do understand the efficiency. Jump with me a little bit, just a little bit. Do you see this one here? 16 PSK. Yes? Are they on a circle? They are on a circle. Can you tell me what is the bandwidth efficiency here? First of all, do you remember what is the bandwidth efficiency? What is the bandwidth efficiency? Bandwidth efficiency is the bit rate, I will refresh your memory, is RB divided what? The bandwidth. Can you tell me theoretically how much is the bandwidth efficiency here? 4 bits per second per hertz. Do not say 4 bits per hertz. It's what? 4 bits per second per hertz. Yes? Did I improve the bandwidth efficiency? I improved the bandwidth efficiency, but on what expense? On the expense that the bit error rate has increased. Why? Because the phases got what? Closer and closer to each other. So if I want to maintain the same bit error rate, if I want to maintain the same bit error rate as the QPSK, what do I need to make the circle? Larger. Did you get my point or not? And what does that imply? I need more power. Do you understand that? Or I need more power, which means what? The EB over N0, that's the one that, did you start, by the way, with the simulation? Or not yet? Be honest with me. See? That's the attitude. That's the wrong attitude, that you keep everything till what? Till the due date. And you can tell, by the way, from your performance in the midterm, there is nothing to brag about. The exam was straightforward. You will see it, the solutions, by the way, are posted. The exam was so straightforward, so straightforward. And it's, the struggle, obvious. Average of the class was 55 or 54 for a graduate level class. How could that be? How could that be? It's so depressing. It was so depressing. It ruined my spring break. Grading it, by the way, was ruining my spring break anyway. But if the results were okay, the pain would have gone. Everything you put it till the last minute, till the last minute, till the last minute when it's too late. Okay, did you understand what I just said? You are going to what? The bandwidth efficiency here will improve 4 bits per second per hertz. But the what? The probability of error will also go what? Will also go up. Which means what? In order to maintain the same bit error rate as the QPSK, I need to what? I need to make this circle what? Bigger and bigger, increase the radius, so that the distance between this, will the distance between this one and this one increase if the radius is bigger? That will, what? That is the whole thing. To try to make the points, what? As far away from each other as possible, to improve the bit error rate. Clear? But that results in what? Increase the amount of power. Okay, distortion, we saw that, for example, in white noise, distortions will be all over the place, equally likely. Are you following? It's like in circles. Clear? But if we do have phase jitter, what phase jitter? What are we talking about? Phase jitter, which phases? Phase jitter between what? The clock at what? At the receiver, and the clock at what? The transmitter, where the point you are going to what? Sample the bits. Did you get this or not? If there is a slight jitter between these clocks, what will happen? This one will move what? This here, the phases. Are you following me or not? Cannot hear you. Okay. Now, the amplitude could also what? Could also get distorted. You see this one, different amplitudes. The phases also could be what? The phases could be distorted due to the what? To the nonlinear. Remember, for the system not to introduce any phase distortion, what should the phase characteristics be? It should be linear, passing through who? Passing through the origin. Is it? Now, in here, this point, this, by the way, the origin. In here, this is what? This is linear. Are you following me or not? But once you get into this region, the system fails to be what? Linear, introducing what? All of these phase distortion. Noise is all over the place. Clear? Oh, the parameter of interest. Again, as I told you last time, I do not want you to forget this one here. They ask a lot of the interviews, especially Qualcomm, when they have openings for what? Internship for RF. By the way, I do have a sample of their questions. If you want, I can send it to you. I don't care. Did you get this or not? What they ask in interviews about RF stuff. If you need it, let me know and I will send it to you. Okay. They ask about EBM. They ask about BSWR and so on and so forth. They just want to make sure that you do understand beyond just the conventional one, which is what? The bit error rate or the signal to noise ratio. What is the EVM? EVM stands for what? The error vector magnitude. In the error vector magnitude, this is how we define it. The absolute value of the error the absolute value of the error. What error? What error? The difference between the what? The actual what? The transmitted symbol, the amplitude of the transmitted symbol, and the amplitude of what? Of the received or the recovered one. The absolute value of the X error divided by what? Some references which you are going to be using. And you can see, by the way, the EBM is inversely proportional to the signal to noise ratio. Question, how come it's square root? How come it's square root? Signal to noise ratio is a what? It's a power ratio, whereas this one is a what? It's a voltage ratio. So you need to take the what? Square root. This equation is straightforward. What does it tell you? It tells you as the signal to noise ratio increases, that results in what? In the error vector magnitude going down. Is that good or bad? That's good. The error vector magnitude goes down. That is good. Now, how do you calculate the EVM of MPSK? We don't have a problem with MPSK. Why? Because all the signals are of the same what? Amplitude. So when you calculate the EVM, it's what? The absolute value of X error divided by the absolute value of X reference, which is what? Which is delta I. Do you understand what this delta I means? This is the difference in which channel? In the I channel, yes? In the I channel, for which symbol? For symbol I. Did you get this or not? How many symbols do we have here? N symbols. Are you following me or not? N symbols. So, by the way, if you want to be precise, this one actually should be what? Should be MPSK, because we are using what? We are using, did I mess up? No, this one is two-dimensional stuff. Did I mess up here? This N should be M, right? 1 second. Yeah, this one should be M, because we do have M symbols. Yes? So this one should be M, not N. But in any case, in here, what is this, by the way? Is this cube MPSK or a QAM? QAM. Why it is QAM? Because you can see that the amplitude and the phase are what? Changing. When you do your simulation, by the way, when the question asks you to simulate QAM, and one of it is simulating QAM, you need to calculate the what? The average energy. Because the energy is going to change. Did you get my point or not? So the axis, instead of being what? EB over N0, it will be what? The average bit energy over what? The noise power spectral density. Remember, N0 means what? Noise power spectral density. Did you get my point? You need to average it because the energy is what? Is averaged. Okay. When you calculate the EBM, you always take the what? The worst case scenario, which is what? Which is the XMX, which is what? Which is the maximum, which is the maximum value of the what? Of the maximum amplitude of the outer signal. Think about it as the outer signal. Clear? Okay, good. Now, I said 30 minutes, I'm running out of it. Another one, which is what? Related to the EBM, which it's also used in the real world. They call it what? The modulation error ratio. MER stands for what? The modulation error ratio. What is this defined as? This is a measure of the average signal power to the average what? Error power. The average signal power, which means what? You average it over all possible what? See, what is, can you zoom in please a little bit? What is this? I square plus what? QI square. What does this give you? When you multiply the what? The I channel square plus the Q channel square, what is it giving you? It's giving you the power of which symbol? Symbol I. And then when you add over what? Over all what? Over all symbols, and you divide by what? The number of symbols, you get the average. But in here, I don't put 1 over n because the 1 over n and the 1 over n will what? Cancels with each other. Did you get this or not? And this is the error. This one is the reference, this one is the error. The advantage of the MIR, by the way, it relates directly to the signal to noise ratio, while the EBM is what? The power must be what? Must be incorporated. Why it must be incorporated? The power. Why? Because some of them have a what? Have different power than the what? Than the other. In here, I'm taking what? The average power. Whereas in here, I'm taking what? The peak. Did you get my point or not? Yes or no? Okay. But both of them are used. Now, the relationship between them, EBM, is equal to the square root of K. This is some hardware implementation margin divided by what? The signal to noise ratio times what? Times the power. Clear? The relationship between the EBM and the signal to noise ratio. Now, another measure for the what? And by the way, all of these measures, the EBM and the MER, is a measure of what? Is also a measure of what? The linearity, how linear your devices is. Clear? Another measure for linearity, which is also used a lot, especially in the spec, when you see the spec of standards, like GSM or the CDMA or whatever, you will see what is known as what? ACPR. ACPR stands for what? The adjacent channel power ratio, which is the ratio of what? The desired what? Desired carrier divided by what? The power from a what? Adjacent channel, or vice versa, by the way. You understand what vice versa means? Means the answer is either what? In positive dBs or what? Negative dBs. Did you get this or not? Yes or no? Okay. So can you zoom back, please, a little bit? Operator, can you zoom back? Okay, no need. Okay, that's fine. Okay, so it's what is the ratio between what? Between the channel and the adjacent to the what? To the channel of the desire. Clear? We would like this one to be what? Small or high? It's the power in the adjacent channel. I want it to be what? Very small. Are you following me? Very small, which means what? The effect of this one is negligible. Okay. This is, again, as I told you, what is this, by the way? 16 QAM. This is another example of a what? 16 QAM. They call it what? 16 APSK. APSK means what? Amplitude phase shift gain. Amplitude phase shift gain. Clear? How many amplitudes do we have here? 2 amplitudes. How many phases? 8 phases. For a total of how many symbols? 16. Yes? With every amplitude, we have how many phases? 8 phases. With the other amplitude, how many phases we have? 8 phases. Clear? Okay, good. This is 16 QAM, 16 PSK, and so on. So now, the MSK. Let me show you the MSK. This one, variation of this one, the one that is used in the GSM, is called what? GMSK. GMSK. GMSK stands for what? Gaussian shaped minimum shift gain. So first of all, let me explain to you the minimum shift gain. Okay. Well, in a QPSK, what would the pulse look like? The data, the I and the Q. What did they look like? In the QPSK, the I and the Q, were they rectangular? They were rectangular. The MSK, they said what? I don't want to go from what? One point in the phase in here. One more time. I don't want to go from here to here abruptly. I want to go around a what? A circle, which means I want the phase to change continuously rather than what? Abruptly. Did you get this or not? Now, if you want to do that, you need to smooth your what? Your pulses. Did you get my point or not? So what do? They smooth their pulses, or they shape their pulses in the shape of a what? A cosine and a sine. Yes? In other words, let me show it to you here quickly. I will show you why they call it minimum shift gain in just a second. Minimum. This is the I channel. Cosine pi t over excuse me, 2TB. Okay, question number 1, first of all. Is this the carrier or is this shaping signal? This is not the carrier signal. Did you understand what I just said? This is the what? A shaping signal. What is this? What type of signal is it? It's a cosine. You follow me or not? Okay, and this is the what? Q of t. Now, of course, it's still what? Delayed by what? By TB. Just like the what? Just like the staggered QPSK. But this one is multiplied by what? Sine. Did you get it? Yes? Sinusoid. And then what do? No. Jeez. One more. I'm sorry. What am I multiplying it with? Cosine 2 pi FCT. What is this? That's the carrier signal now. Okay. And then here what? Sine 2 pi FCT. Did you get this or not? This is what? A carrier signal, but they are what? It's the same frequency, but they are what? 180 degree out of phase. Did you get this or not? Did I say 180 degree? I'm sorry. 90 degree out of phase. Clear? A sine and a cosine. Okay, then what do? So what is the S of t? S of t, this is S of t, yeah, is equal to what? I of t, so there is a minus sign. I of t, cosine, pi t over 2tb plus what? Times cosine, 2 pi fct minus q of t, again delayed version, times what? Sine, 2 pi t over what? 2tb sine 2 pi fct. Clear? Clear? Okay. And when you get what? When you combine this, this can be combined into what? Into the following. Cosine 2 pi fct plus some what? Plus some, this is sk in the kth interval. In the kth interval, okay? In the kth interval, sk of t. This is the kth interval. Bk times what? Pi t over 2tb plus what? Plus some phi of k. If you combine them, you get the following here. Where b of k, where b of k is equal to plus 1 if I of t and q of t. The q of t is the delayed version. Q of t is the delayed version. Is both what? Sorry, are both of same sign? And it's equal to minus 1 if they are what? And the theta k is either what? Theta k is either what? It's either 0 or what? Pi. Now, I want you to tell me what is the instantaneous frequency. What is the instantaneous frequency? I'm still waiting. The instantaneous frequency in here. Let's assume bk equal to what? Bk or bk equal to what? 1. Which means what? The I and the q are what? Are the same. What is the fi? What is the instantaneous frequency of this? Is what? Is f sub c plus what? 1 over what? 4 dB. Did you understand where the 4 came from? Where? I need here 2 pi and I need to multiply this by 2. So 2. Then the f will become what? bk is equal to 1. The f is what? 1 over t sub b. Yes? And for bk equal to -1, what is the frequency? F sub c minus 1 over p for t sub b. Yes? This is if what? If they are of the same sign, this one is of they are what? Different sign. What is the separation? The two frequencies are separated by what? How much? 1 over 2 TB. Which is the what? Which is the minimum frequency separation required to maintain what? To maintain what? Orthogonality. Are you following me or not? Orthogonality, what? It makes it easier on the demodulator to what? To distinguish between the I and the Q channels because they are what? They are going to be orthogonal stuff. These are the minimum frequency. That's the minimum. You cannot get any minimum than that. Clear? Clear? Okay. This is the MSK. By the way, I want you to notice, I want you to see this. No, first of all, I need to show you another graph so that you can see the difference. 1 second, please. I need to show you one thing. This is the QPSK. Do you see the phase changes? Do you see the phase changes? Is it abrupt? I want you to see this. This is the resulting of what? What is this a result of what? This is this one. What is it? Is this one? Yes? Tell me. Do you see the phase changes? I'm not sure. Did you get the point? Did you get the point or not? This is what I'm getting. Yes? By the way, is this a single tone? This is not a single tone. This is not a sinusoid. Are you following me or not? This is not a sinusoid. But do you see sudden changes in the phase? Or is the phase continuously changing? Continuously changing, which means what? Going from one symbol to another symbol. What are you, by the way, is the amplitude changing? The amplitude is not changing. You notice, by the way, the amplitude here, I put it what's constant. You put A, for example. Did you get my point or not? The amplitude is not changing. And the transition from one symbol into another symbol is what? The phase is going to change what? Continuously rather than what? Abruptly. Clear? Okay, you get this one here. Is this a constant envelope or not a constant envelope? Constant envelope all the time. Why? Why? Because the amplitude is what? It's fixed. Did you get my point? Yes, there is no sudden changes between the phases. So they allow them to use the what? They allow them to use the power amplifier in its highest efficiency level. Yes, they don't worry about what? Non-linearity, because the amplitude is what? Is fixed. Clear? This is the trajectory of changing of what? Of changing the phase. You go either what? You go up or you go what? Down, depending on what? Depending on the whether the BK and whether the BK is 1 or whether the BK is what? Is -1. You go smoothly, linearly. Did you get this or not? The phase is changing in a what? In a linear fashion. Clear? Okay, good. Now, the GSM people, they modified it a little bit. Before they what? Before they shape it using what? They have sinusoid. They what? They shape it using a what? A Gaussian. What does a Gaussian look like? Gaussian. Huh? Yes or no? Is it smooth? Also smooth. Are you following me or not? Yes? They can afford to do that. Why they can afford to do that? Remember, once you shape the signal, what happens? You are going to introduce what? You are going to introduce intersymbol interference. Did you get my point or not? But they can afford that. Why? Because the bandwidth that they are operating was 200 and what? 70 megahertz. Did you understand that or not? 270 megahertz in the what? In the cellular band. Did you get this or not? Okay, so they were able to what? They were able to support what? Did I say 270 megahertz? I'm sorry, 270 kilohertz. It's not megahertz. 270 what? Kilohertz. They can afford to what? To support higher rates, and which means what? More channels in a given what? In a given band. In a given band, they support what? 8 channels using TDMA, using time division multiplexer, as opposed to what? Roughly 3 or 4 channels in the case of what? In the case of the TDMA system in the US. Because the TDMA system was what? Was a narrow band as compared to the what? As compared to the GSM. Clear? No response. Clear? Okay. Now I want you just to see this and tell me this is the most important part so that you can see it. This is what? This is the what? This is the dotted line is the what? Is the MSK. The GMSK. Do you see the GMSK? It's dropping even faster than the what? Than the MSK. Did you get this or not? It is dropping faster than the what? Than the MSK. MSK is what is this? The solid one. The solid one. That's the QPSK. The MSK is the what? Is the dotted line, this dotted line. And you can see the what? You can see that the main lobe has what? Wider a little bit. You follow me or not? Wider. To maintain what? To maintain the orthogonality. Separation between the frequencies requires what? More bandwidth. Did you get this? Okay. But on the good thing is what? Is that the drop will become what? Will become much faster. The drop into the adjacent channel will become much faster than the QPSK. Notice, by the way, the QPSK, it lingers all the way to what? All the way to multiple channels on this side. Clear? Okay. This is, again, you can see it clearly, the degradation of what? The degradation of the side lobes comparing the GMSK and the QPSK. What is this? That's the BER curve. This is EB over N0 as compared to what? As compared to the bit error rate. What do you notice? You notice that for the same bit error rate, GMSK require a little bit what? GMSK require a little bit more power. How much power roughly? For 10 to the minus 5? 10 to the minus 5. The roughly is what? 2 dB, 2.5 dB, and so on and so forth to get the same bit error rate. Now, listen to me. This is very important because I don't want you to do something like this in the simulation. In the simulation, when the question asks you, for example, to simulate 100,000 points, 100,000 bits, I don't know how much is he asking you the question is asking you to simulate how many bits, but let's assume it's 100,000 bits. Now, with 100,000 bits, what does it mean, the bit error rate? What is the worst? You are simulating what? 100,000 bits. Yes? The worst case scenario is what? Is that you get what? The bit error rate. The best case scenario, the bit error rate will be what? Will be 10 to the what? 10 to the minus 5, which means what? Like 1 bit out of what? 100,000 bits is in error. Did you get this or not? I don't want you to use a scale like this. And your curve will be what? Will be only this portion. Ugly. Did you understand what I just said or not? I want you to what? Start from here at what? 10 to the minus 5. And then go 10 to the minus 4, 10 to the minus 3. And then what? Vary the EB over N0 on this side. Did you get this or not? In other words, I don't want you to compress, because these values you are not simulating. You are just extending the curve by hand. Not sure, did you get my point? See, because I'm asking you in the simulation to compare this with the theoretical one. The theoretical one will generate these curves. The simulation will generate only this portion, which means the curves will look what? Ugly. One of them is short, the other one is what? Long. Not sure, maybe I'm not expressing myself properly, but did you get my point? Did you get my point? Start from what? 10 to the minus 5 here. Do not go all the way to what? 10 to the minus 20. Ridiculous, 10 to the minus 20. Did you understand what I just said or not? This is the author. This is here for you. He gets what? All the way to the 10 to the minus 20. Ridiculous. On a wireless, you are going to get 10 to the minus 20? Where is it? In his dream? But anyway, I don't want you to do that. Clear? I want you to limit yourself to what? 10 to the minus 5, and then what? 10 to the minus 4, 10 to the minus 3, and so on and so on. Your curve should be what? Should be smooth and looks like this. Okay. Now, of course, there is a limit to how much you're what? How much are you familiar with this equation? S equal to what? Not S. C equal to what? B, or W, sorry. W log 1 plus the what? Signal to noise ratio. Are you following me or not? What is this? That's Shannon's theorem. Now, what did he say? He said that you cannot transmit at a what? At a rate higher than what? Higher than the what? Than the capacity, and still expect what? Can you transmit at a rate higher than the capacity? Yes, you can. But the probability of error will approach what? Will approach 1. Did you get this or not? Are you following me or not? Probability of error means what? Whatever you are transmitting, everything will be what? Wrong. Clear? Okay, so the idea is what? The idea is to try to what? To achieve a reliable transmission. Now, in this equation, if you take this equation, so you have RB is equal to what? W, assume the RB equal to C, RB, W, log 1 plus the signal to noise ratio. How do you modify this? W, log 1 plus, what is the signal to noise ratio in terms of EB over N0? Are they the same? No. So what is it? It's EB over what? N0 times what? W times what? RB. Did you get this or not? Yes or no? Now, RB brings the W here, so what do you get? You get RB over what? W equal to what? Log 1 plus EB over what? And 0 times what? RB over what? W. Okay, which means what? EB over N0 is equal to what? The log, this log is to the base what? 2. So what do I have? I have, help me, 2 RB over what? W, 2 to the RB over W, help me, minus 1 times what? Divided by RB over what? W. Clear? And that allow you to what? Allow you to sketch the following curve. This is what? EB over N0. This one is what? RB over what? W. What do I call this? The bandwidth. Efficiency. And what do I call this? The power. Efficiency. Yes? The curve, this, will be like this. This will be like this. Are you following me so far or not? Or you lost me? You must have seen this before in the communications classes. 535, did you see this? I don't know what you study in 535. This region is what? By the way, this is not 0. Do you understand what this means? It's not 0. RB over W. This one means what? 1, for example. 1 bits per second per hertz. Yes? As you go this way, what does it become? What does it become here? Bandwidth efficient or bandwidth inefficient? Inefficient. Why? Because the RB over W will become what? Fraction. In here, the RB over W. In other words, this is what? 1. This is what? 2. This is what? 4. Are you following me or not? What is this on this side? What is it? 1/2? 1. Are you following me? Okay. What is this side? Everything on this side is what? Is possible. Possible means what? You can design a system that will provide you with the rates or with the power efficiency or the bandwidth efficiency as you wish. Clear? Okay. These are what? These are the MPSK and the what? The QAM. What can you tell me about the MPSK and the QAM? Based on this, they are what? Bandwidth efficient, but they are not what? Power efficient. They are not power efficient. They are bandwidth efficient, which means they are going to be used when we do have what? Larger bandwidth or smaller bandwidth. Smaller bandwidth, and I'm trying to what? To cram as many data as possible on the given bandwidth. Did you get this or not? On a bandwidth challenged. Whereas this one, what is this? These are the what? MFSK. MFSK stands for what? Multi-frequency shift keying, including the what? Including the MSK and including the what? The GMSK family. What can you tell me? They are what? They are not bandwidth efficiency. They are more of a what? Of a power efficiency rather than what? Rather than the bandwidth efficiency. What is the ultimate number here? Can you tell me what is the ultimate number? The ultimate number is this point, which is what? Minus 0.6, 1.6 dB. If you take the log, if you take the limit as W approaches infinity, which means what bandwidth? Infinite bandwidth. Realistic or not realistic? Not realistic, but that's in the limit. He shows us that EB over N0 approaches what? Minus 1.6 dB. Strange enough, really strange. Is this high or low? This is extremely low. He said even if your EB over N0 is minus 1.6 dB, you can still achieve what? By the way, when it's minus 1.6 dB, what does it mean? It means the noise what? What am I comparing here? The bit energy with the what? How do you compare the noise energy, the signal energy with the noise power? My dear, how? This is unitless. N0 is not the noise power, it's the noise power spectral density, which is what? Watts per what? Per hertz. Watts per hertz is what? It's joule. So you are comparing the bit energy to the what? Noise energy. Yes? Which one is larger? The noise energy or the bit energy? Noise energy, because this one is negative dB. Yes? So he said what? He said there exist some ways, some coding schemes that allows you to what? To transmit even if the noise is what? Much stronger than the what? In energy-wise, much stronger than the what signal, you can still achieve what? A reliable transmission, which means what? The probability of error approaches what? Approaches 0. Did you get this or not? Yes or no? Okay, this one you will take it in EE, the coding stuff or some in EE 565 and EE Forgot. 560, maybe 9, 8, maybe 8. A, B. This is on information theory. This is on coding theory. Clear? Right now, I'm not interested in neither one of these. Do you understand? Why? Because there is a word theory in it. Let's not get into theoretical stuff. But I need you to understand the trade between the what? The power efficiency versus the what? The bandwidth efficiency. That's the ultimate thing from this study. Clear? No response. Clear? Okay, good. Now, this you can read it on your own, and the definitions of the what? Of the definitions of this, the one I just showed you. This is the systems. By the way, the data rate is what? 270 kilobits per second. Bandwidth is how much? 200 kilohertz compared to the North America, which is the bandwidth, what? 30 kilohertz. Question, by the way, question. Why is it 30 kilohertz so small? This is the second generation, not the third generation or the fourth generation. Second generation. How come it's so small? That was the same band that was allocated to the analog phone. Did you understand what I just said? Now, when they brought digital technology, they do not expect all the customers to throw their what? Analog phones right away. So at the beginning, they use the same band. Some frequencies are what? Time division multiplexed, and some frequencies are used as what? Analog, using what? FDMA, frequency division multiple access. Did you understand what I just said or not? The GSM people, that started in what? In Europe. It's the European Federation here. So they have freedom to choose what? Something which is different than the analog stuff. Clear? Clear? Okay, good. We are done with this. Now, one more thing I need to show you. One more thing before this, which is this. Let me just give you this as you will study it in EE 535, I think, or EE 635. But I just want to give you the principle. Why? This is the technology that is going to be used in the fourth generation Wi-Fi, for example, or what? Or the third and the fourth generation of what? High-speed access, high-speed data access using your cell phones and so on and so forth. I want you to understand, first of all, this one here, and what is the difference between this orthogonal FDM and FDM? FDM. FDM stands for what? Frequency division multiplexing, which was used in what? Which was used in the analog telephony. For example, FDMA, frequency division multiple access. In frequency division multiplexing, this is what they have. They take the band, this is F, and they divide it into what? Non-overlapping what? Frequency. Are you following me so far or not? Non-overlapping frequency separated by what? By guard band. This technique requires what? Wider bandwidth. Did you understand what I just said or not? In OFDM, this is what they have. In OFDM, the bands are what? Are overlapping. Did you get my point? However, when they sample each carrier, subcarrier, all the others will contribute what? 0, which means what? There is 0. A new terminology that we learned today. ICI. What does ICI stands for? This is not intersymbol interference. This is what? Intercarrier interference. Did you understand that or not? Okay. Forget about this. I will show it to you in a minute. But did you get at least the difference between FDM and OFDM? In OFDM, the channel do what? Overlap with each other. Did you get this or not? To what? To save on the what? On the bandwidth. But at each subcarrier, the contribution of other subcarriers is equal to what? 0. Did you understand? To maintain their what? Orthogonality. They are orthogonal, which means what? At the receiver, you could what? You could multiply each one by that carrier, and there will be no interference from one to the other. Clear so far? Okay, let's get into a little bit more detail. But did you get the idea here? Let's get a little bit more into detail. Listen to me. What was the goal? The goal is to try to transmit at a much faster rate. Yes, those rate of your cell phone or something is not good enough. Are you following me or not? How much are you getting using your cell phone right now for data? How much are you getting? You are getting roughly what? It's the old version, like second generation or third, you are getting what? 20 kilobits per second. For third generation, you might get what? 100 or something. Very little. They wanted to get into what? Into megabits per second range and so on and so forth. Now listen to me. The higher the rate, the higher the rate of your data, it means the bandwidth occupancy of your data is what? Wider. If the bandwidth of the channel is narrower than the bandwidth of the what? Of the data, what will happen? What will happen is that you are going to experience what? Intersymbol interference. Are you following me or not? And the fading will be what? Frequency selective fading, which means what? It's terrible. Did you understand what I just said or not? It's going to be terrible. Some frequencies are not going to be what? It's the channel will behave. In other words, h of omega will be equal to what? At 0 at some frequency. That's what it means by what? Frequency selective fading. Clear? So what did they do? Are you following me so far or not? Or you are losing me? Tell me the truth. Are you losing me? I have a high-speed data. High-speed data means what? The bandwidth occupancy is what? Large. Yes? The bandwidth of the channel is not as large because it's limited. This is what they have, what is given to these services. Are you following me or not? What will happen? If the bandwidth of the channel is much smaller than the bandwidth of the data, what will happen? The data get what? Smeared. In the time domain. In the time domain, the data will get stretched, introducing what? ISI, the intersymbol interference. Yes or no? So what did they say? They say, let's take the original data, which is at high speed, and change it from a serial data into a parallel data. Doing like this, listen to me. Let's assume the data is what? Even odd. Just an example, even odd. The even goes up, the odd goes down. Even goes up, odd goes down. How much did you divide the rate? You divided it by 2. Yes or no? Could you divide it by 10? Which means what? One bit goes here, the next bit goes here, third bit goes here, which means the bit rate has what? Dropped. And you modulate each one of these lower rates on a subcarrier. On a subcarrier, those subcarriers are chosen to be what? Orthogonal. Orthogonal does not mean like this. It means like what? This. Did you get my point or not? Because if it is this, it means what? We haven't done anything. Why this one will not work? This one requires what? Larger bandwidth. The whole idea is that the problem was caused because I don't have what? Large bandwidth. Not sure. Did you get my point? Did you get my point? The whole idea, they said what? Let's the channel what? Overlap with each other. I don't care. But the problem is that what? At the center frequency, this is the frequency with the frequency domain. At the center frequency, I want the contribution of what? Of the other channel to be equal to what? 0. Did you get my point or not? Did you get my point or not? Which means what? Which means that the frequencies are what? Are orthogonal to each other. Clear? Are orthogonal to each other. Now, this does not mean, this is not the same as ISI. This means what? ICI. There is no interference from what? One subcarrier to another subcarrier. Clear? They modulate, so they took the data, this is the data, they take it into a what? Serial to what? Parallel. Yes? They what? Are you following me or not? And for each one of them, they modulate a what? By the way, they modulate a cosine and a sine. So instead of saying that, I'm going to write this. E to the j, pi, 2 pi, yes? N, t, k, t. Where k is equal to what? K is equal to what? 0, 1, 2, all the way to what? N minus 1. What is the n? What is the n here? Is the number of what? Subcarrier. Do you understand what this means? When I multiply by e to the j, what does it mean? It means what? Sine and cosine. Did you understand that or not? In other words, one data stream is going to what? Modulate a what? A cosine. The other data stream is going to modulate a what? A sine. Yes or no? But at the same frequency. Clear? Same thing with this one. Same thing with this one. But different what? Different frequency. Here, what is the k? N minus 1. Yes? What is the separation, by the way, between the frequencies? What is the separation between the frequencies? Can you tell me? You are losing me here. What is the separation between the frequencies? Now remember, the frequencies is what? Is 2 pi f. So the f is what? Is k over what? Nt. Yes? K equal to what? 0, 1. In other words, 1 over nt. The other one is what? 2 over nt. So what is the separation between them? 1 over nt. Where n is what? Where n is the number of subcarriers. Did you get this or not? In doing so, what did they do? They reduce the what? They reduce the bit rate in here by what factor? By a factor of n, which means what? To support this data stream, you don't need a what? A much wider what? A much wider bandwidth. Notice, by the way, they are going to add this. Are you following me or not? They are going to add all of these things. But at the receiving end, can they separate them? At the receiving end, if they multiply them by these again, assuming, of course, they are what? Synchronized, yes or no? They will be able to separate the what? The data stream, and they will be able to what? Combine them again to get what? To get the serial data stream. You lost me here? You lost me here or not? Yes or no? That will work only if those are what? Are orthogonal signals. Yes? Okay. What is the problem with this? No, besides synchronization, dealing with what? With the par I want. Is the par high or low? The par, which par stands for what? The peak power to average power ratio. Will it be high or will it be low? It will be high. Are you following me or not? Which means what? You need to be very careful in designing your what? Your power amplifier. Otherwise, you are going to get all of these what? Side lobes. And the side lobes, by the way, they will not be what? Orthogonal with the what? Original frequency separations. Clear? No response. Clear? Always remember the rule of thumb, which is the following. If the bandwidth of the data is less than the bandwidth of the what? Of the channel, you are not going to get what is known as what? Selective frequency, selective fading. You will get what is known as what? Slow fading or flat fading, which is what? Which is not as severe as what? Selective fading. All of this, by the way, you will take in this. I cannot cover 2 courses in 1 course. I'm losing my voice here. Did you get this or not? So in here you will study, I'm sure, the flat fading, the frequency selective, and so on and so forth. Slow and the fast fading, and so on. Clear so far? If the bandwidth of the data is greater than the bandwidth of the channel, you are going to suffer what is known as what? Frequency selective fading. In a frequency selective fading, the characteristic, this is h of f, there is a possibility that you will get something like this. Some frequencies will fade all the way to what? 0, which means what? All the data during that time in which the channel is experiencing frequency selective fading is what? Lost. Did you get this or not? Yes or no? No response. Yes or no? Okay, good. Now, did you get the general idea? The general idea. Now, I will be posting tutorial if you want to learn a little bit more about OFDM tutorial, but I really do believe that it will be covered in either one of these 2. So if you are, I think this one will be offered in the fall. In the fall? Yeah, in the fall. So if you are interested in learning more about OFDM and the new generations or something like that, I urge you strongly to take 635. The only objection I have on these 2 courses, these sequence courses, is that there is no project in them. And I don't understand this, but I don't care. I'm not going to go and argue with him. Do you understand that? My feeling is that there should be what? Project decided in terms of what? Channel modeling and so on and so forth. Clear? But apparently not, so I don't care. Clear? Clear? Okay, good. Now, let's get to the more interesting stuff. What are we going to do? From now till the end of the semester, we are going to pick up those components in the transceiver. In the transmitter, the only component that we will study is the what? Is the power amplifier. Why? Because it is the most problematic device, and besides, all the other devices, for example, oscillator or what? Or the synthesizer, are you following me on the amplifier? We are going to see them anyway at the receiver side. Did you get this or not? And at the receiver side, the design is much more challenging Why? It is much more challenging. Because noise is going to be there, interference is going to be there. At the transmitter side, we don't have those kind of problems. Clear? Okay. The power amplifier per se is a course by itself. It's a huge topic. Did you understand that or not? But I'm going to only concentrate on the basic, most important concepts in the design, and we see how it goes from here. Clear? No response. Clear? Okay, good. Now, let's understand what is the power amplifier. Why power amplifier? The answer should not be why not. You need to elaborate a little bit, not why not. What is the purpose of the power amplifier? The purpose of the power amplifier is to provide the signal, the transmitted signal, with enough amplification to reach the desired transmitted power. Now you have to remember, the power is going to lose its strength as it propagates. So if you want to provide coverage means what? Provide range for your services, for your wireless services, you need to You need to have the right power at the transmitter. Clear? However, we need to We need to provide this power to the antenna while at the same time preserving the integrity of the modulation. What does preserving the integrity of the modulation means? Means that we need to make sure that the modulation that we are using is confined within the Within the transmitted bandwidth. Do you understand it or not? We don't want to introduce distortion, whether it's AM distortion or PM distortion and so on. So phase modulation or AM modulation distortion. Did you get this or not? Now, what is it going to do? A power amplifier is a device that will change the DC power to RF power, not the input. What is the input to the power amplifier? Is it RF? The input to the power amplifier, is it RF? It is RF. The difference, the ratio between the power here and the power here, what did we call it? The power gain, which is G sub P, yes? But that's not the purpose of the power amplifier. The purpose of the power amplifier is to convert the The DC power. Now you might say, where is the DC power coming from? You need to You need to bias this amplifier. You need to power it. You follow me or not? We need to transfer or to convert the DC power to an R power. That will take me to the first definition that you need to understand, which is what is known as the efficiency. Sometimes they call it the drain efficiency. The drain efficiency. Clear? What is the definition of the drain efficiency? The output power. What power? When you say output power, what power? The RF at what? At the fundamental. Are you following me or not? At the fundamental. The output power. At the fundamental. The RF power divided by the DC power. Did you get this or not? Now, some other people define in the industry, they define also another one, which is called the power added efficiency. They call it PAE. PAE stands for the power added efficiency. Clear? Let's understand what is this. The power added efficiency is the output power. Is this the RF? RF power minus PN, which is also the The RF power divided by The DC power. Now, if you factor out the output power divided by the DC power, what remains? P out divided by PDC is Is 80. So it's 80 times 1 minus what remains? 1 over GP. And if GP is high, this term is Negligible. And you end up with You end up with the drain efficiency and the power added efficiency to be almost To be almost the same. Did you get this or not? Yes or no? Okay, so keep in mind always that the amplifier is supposed to Is supposed to convert the DC power to the To the RF power as efficiently as possible. Yes? When the DC power is equal to the RF power, what do we say? Efficiency is 100%. But if it is below, what happened to the rest? What happened to the rest of the power? All the rest of the power was Dissipated as Heat in the In the transistor. Did you get this or not? In this case, in the In the MOS. Did you understand what I just said or not? I don't want that. I don't want that. I want what? All the DC power to be what? Converted to the what? RF power, which means what? It means that the dissipation in the transistor itself is what? Zero. Can be done or not can be done? Cannot be done. But there are some designs which are approximating very close to what? Very close to 100% efficiency, which I'll show you in just a second. But on what expense? We will see that as the efficiency goes up, the power delivered to the antenna goes what? Goes down. Did you understand what I just said or not? But it will not be clear until I show you examples. So just be patient. I will show you that in just a second. Did you get my point or not? Okay, good. Now, let's see. What is the power amplifier? Do we need a matching network here? Yes, we need a matching network here. Why? Because if the output resistance or the output impedance of the power amplifier does not match the what? The Z naught, for example, of the feeder cable, we are going to have what? We are going to have power losses. Do you follow me or not? So we need to have what? A matching network. And that matching network should not introduce additional what? Losses, which means what? It's either a what? A transformer or what? Or some kind of what? An LC matching or a pi or whatever that we discussed earlier. Did you get my point or not? Okay, let me show you one thing before we continue here. Let's take just one example. Let's assume I have a power amplifier here. Okay, and let's assume this is the load. And the load is 50 ohm. Just an example, 50 ohm, which resembles what? Which resembles the Z naught for a what? For a feeder cable or antenna or whatever. Clear? Okay, and let's assume it is desired to provide or to supply the load with 1 watt power. Yes? So the power is what? Is 1 watt. I want to what? I want to deliver, not supply, deliver the load with 1 watt. Yes? Help me. What is the voltage here should be? What should the voltage be? The voltage across the 50 ohm. You are losing me? Do not lose me. I still have time. The class is not over yet. Concentrate. I want to deliver a 1 watt power to this load. What is the voltage between this? In other words, what should the output voltage of the power amplifier be? Now remember, this is an RF power. Yes? So what do I have? V, let's call this one V naught. V naught square over what? 2R. Why 2? Why 2? This RF, sinusoid, this RMS. Yes or no? Okay, equal to what? 1, which means what? V naught equal to the square root of what? 2R, which is what? 10 volts. Ridiculous or not ridiculous? The voltage here is what? 10 volt. This voltage supply, we will see that the voltage supply is what? Am I going to use 10 volt power supply? Of course not. I'm going to use what? With this new technology, with the most advanced technology, we use what? 1.8 volt or 2 volt, or let's say, worst come to worst, 5 volt. So how am I going to get 10 volt here? Did you get my point or not? Oh, so, by the way, what is the current? What is the current? The current is yes? No response. Yes? So what is I0? Did I mess up? 2 by what? 50. Which is what? 1 over 25, so it's what? 1/5, which is what? 0.2 amps. 0.2 amps? Yeah, 0.2 amps. Agree? Yes? Okay. Ridiculous, the voltage, ridiculous? The current, let's not worry about the current right now, but is the voltage ridiculous? What do I want? I want to reduce the voltage. Yes? What do I do? I use a what? Some kind of a what? A matching circuit in here. So if I use, for example, like this. This is the power amplifier. And let's assume I use this. What is this? This, oh, sorry. Yeah. This is what? The 50 ohm. What should this one be? I want 10 volt in here. but I want what? Much less in here. So let's say, for example, this is 1, 2, 4. Just an example. Yes? What is the voltage here? 2 point what? 2.5 volt. A little bit what? More reasonable. Yes? Cannot hear you. Okay. Notice, by the way, I want the resistance here, by the way. The resistance is 50 ohm. Now, when the voltage reduced by 4, what about the current? The current will increase by what? Now, the current at output of what? Is how much? Agree or not? Yes? So, what is the big deal? So, what if it is what? 0.8? By the way, is this large? Let's see what. If there is, at the output of the power amplifier, just an example, let's assume that there is a what? There is a parasitic resistance, very small resistance, 1 ohm. Let's assume that it's 1 ohm. Are you following me or not? So let's assume at the output of the power amplifier, assume output of power amplifier, there is a 1 ohm parasitic resistor. Yes? Yes? How much power will be dissipated? How much power will be dissipated? So the power dissipated. I cannot write faster than you talk. Let me, power dissipated in this resistor. I'm still waiting. Is what? Is 0.8 square over what? Times what? Which is what? 0.32, which means what? 32 milliwatt. It is supposed to provide how much? How many watts to the load? 1 watt. 320 milliwatt will go what? Will go wasted, dissipated in a what? In a parasitic capacitor. In a parasitic resistor. Did you get my point or not? So designing the matching circuit will become what? Will become crucial in this case here to what? To match the output of the power amplifier to the what? To the antenna input or to the feeder cable input. Clear? Okay, good. Now, what requirements? When you talk about power requirements, of output power, in other words, the spec, when you look at spec of the power amplifier, you look at what? Output power. How much output power? Output power depends on what? Depends on the standard. What, for example, if you are using Bluetooth, it's what? 4 dBm. How come it's too small? How come it's too small for the Bluetooth? The coverage is what? It's limited. We are talking about what? We are talking about less than 10 meter difference. Are you following or not? The Bluetooth is a what? Standards that sometimes they call it a what? A personal area network or a body area network, because you are going to put the devices on your body, either on your wrist or on your phone or whatever. Okay. Whereas for example, the wideband CDMA, which is the 3rd generation, it's what? 27 dBm, which is what? Which is much larger than it's about whatever. Okay. The power gain provide antenna with adequate RF power typically is about what? 10 to 40 dB. These are typical values. Linearity. How do you measure linearity of a power amplifier? You measure the linearity of the power amplifier from looking at what? The ACPR. ACPR stands for what? The adjacent channel power ratio, by looking at what? The dB compression. If the 1 dB compression is what? Is high, what does it mean? It means that the power amplifier is linear for a what? A wide range of input powers. Yes or no? It's the IIP3. The higher the IIP3, it's what? The power amplifier is what? Is linear, more linear. Did you get this or not? Okay. So the linearity is what? Linear. I skipped this one. One more time. I skipped this one. I'm sorry. Efficiency. We would like to minimize the power wasted in the transistor. Convert the entire DC power to the what? To the RF power. That's the efficiency. Linearity. This is especially important in what? AM or even PM system to prevent spectral regrowth and hence minimize what? Interference. Minimize interference onto who? Onto the adjacent channels. Are you following me on that? By the way, you might say, what do I care about other channels? That's their problem. Their problem is also your what? Your problem. When their design, results in what? When the results in what? In adjacent channel which interfere with yours. Did you get this or not? You cannot say what I don't care what happens to the other. Clear? Okay. By the way, another measure of the linearity is to look at what is known as what? The emission mask. Remember the emission mask? The power spectral density, which is what? It's like a brick wall, some brick like this. I showed it to you earlier in the semester, like this. Something like this. What is this, by the way? What am I sketching? This is the frequency. What am I sketching here? The PSD. What is PSD stands for? The power spectral density, which is the what? Power emitted per unit what? Per unit hertz. And if it is what? If it is in here somewhere, like this, then it means what? Then it means that your system or your power amplifier is what? Is linear. You are not generating those side lobes. If it goes...
Professor, yeah, we have 5 minutes.
Yeah, thank you. The time goes very quickly. If it goes up there, it means what? It means that you are generating what side lobes that will result in what? That will result in interference, adjacent channel interference, and so on and so forth. Impedance matching, this is the one that I just told you about, whether the PA is connected to the antenna or whether it's followed by a what? A filter. Whether it's followed by a filter, we might need a what? Matching network. Why is it followed by a filter? To what? To filter the what? To filter the side lobes that have been what? Regrew from what? From the nonlinearity. Now, but keep in mind that the filter you introduce will also introduce what? Losses, insertion losses. Even if your filter, by the way, is an LC type filter, still there are parasitic resistors that results in some losses, insertion losses. Output power control, this is important only in what type of systems? In CDMA, not in TDMA or in FDMA. Why? One more time. In a CDMA, all those mobile devices are transmitting at the same time using the same what? Frequency. Are you following me or not? You need to what? You need to apply a power control mechanism so that the what? The receiver that happens to a mobile unit that happens to be close to the what? To the base station does not overwhelm or does not block the receiver from recognizing or sensing that there is a signal from what? From a mobile that happens to be a little bit farther away from the what? From the base station. We discussed this earlier in the semester, if you remember, which I doubted. Did you get my point or not? So what this means, you apply a power control mechanism in which if the mobile unit is far away from the base station will tell it what? Increase your power. If it is close enough to the base station tells the mobile unit, lower your power. Are you following me? I don't need that much power from you. You are close to me. Did you get my point or not? Okay, such that the receipt power is almost what? The same, regardless of what? Regardless of whether you are far or whether you are what? Slow, because close, because the transmitter power will be different. Clear? Okay, good. Now, the performance measures I just explained to you. This is what? This is the mask that I was telling you about. When you see this, what is it? Minus 20 dBc, minus 20 dBc, minus 28 dBc, minus 40 dBc. What is the dBc stands for? dB with respect to the what? With respect to the carrier. The carrier is the center. Did you get this or not? Yes or no? Okay, good. By the way, if you don't put DC, that is fine. It's still dB. But don't put dBm. Because when you put dBm, it means what? You are measuring power. This is power spectral density. Did you get my point? Okay, good. This is a sample mask for different wireless standards or cellular standards and so on and so forth. Now, what are we going to study? What type of power amplifiers we will study? We will study 2 types of power amplifiers. The first one, which is called what? Current mode power amplifiers. In a current mode power amplifiers, the transistor is going to behave as a current source. Did you understand what a current source is? This, by the way, now it comes all of the things that you studied in electronics or the thing that Aaron reviewed for you from the beginning of the semester till now. Clear? These are called what? Current mode power amplifiers. We are talking about what? The transistor is acting as a transconductance. Everybody familiar with the transconductance? What is the transconductance? I cannot hear you, sir. Okay, so the ratio of the what? Of the current divided by what? The voltage at the input. The current at the output divided by the voltage at the input for a constant what? For a constant drain current. Did you get this? Sorry, for a constant drain voltage. Did you get my point? Okay, we'll get to that shortly. Which means what? What are we operating? In which range we are operating? We are operating in the saturation range. In the other one, by the way, the classes are what? A, B, and C. We will only talk about what? A, B, and C. A, B is somewhere between B and C. We will see that the circuits, the amplifier, is the same for all classes. What differs is where am I going to bias my amplifier? Did you get this or not? And it's what is known as what? The conduction angle. We will see that in a class A, we are going to have a 360-degree conduction angle, which means what? The transistor is conducting all the time. In here, we will see that it's what? 180 degree, which means the transistor will be what? On, off, 180 degree on, 180 degree off. C is what? Less than 180 degree. Clear? We will see that, and we will see
Professor,
that.
we are out of time.
Out of time. Nothing I can do about it. We will continue next time.
This concludes today's session of EE 544 on Tuesday, March 25th, 2014.